Believe that ultimately, once we attain the biological immortality, which I believe is inevitable, that will occur, that cells will be programmed in such a way that they won't get old anymore, they won't turn into cancer, our vascular system will maintain its youthful, pliable tone so that there will be no more atherosclerotic disease, will control autoimmune diseases that are so rampant in elderly people. People will live literally forever in a good, healthy state, but that risk of accident and trauma and just these unknown problems will motivate people to want to go a step further, and that is develop artificial intelligence that can then take our biological emotions, which are nothing but chemical reactions in our brain anyway, in our memories, in our identities, and transfer those into an electronic format that can then be backed up and stored in many places so that we will essentially have physical immortality. No matter what happens to that primary being, there will be backup disks spread out in as many places as you can afford to keep them stored.
And I became convinced that intelligence is not really such an amazingly fancy trick. Not that it's trivial by any means, but I think there's a lot of ways to make an intelligent system. Nature has discovered one, which is embodied in the human brain, and nature discovered it kind of haphazardly. The way that nature discovered to achieve intelligence has pluses and minuses, which we're all very familiar with. And it seemed to me that you could make superior intelligence to humans in digital computers. Then once you have that intelligence, then all the other problems become easier. Then time travel is easier, making humans immortal is easier, because you have either a superior digital mind or a different kind of digital mind, which is complementary to yours, to help you discover everything you want to discover.
And what I'm hoping to catch is those three neurons, as they develop, is their neurites spreading out and connecting up. And what I'm hoping is that we can build models of small cortical circuits in order to understand how the brain actually wires up and develops and learns and stores information from watching things like this. Because it's sitting on top of an electrode there too, we can also observe them electrically. So we can see all the electrical activity in the network, and we can see the physical structure as well. And so I'm working on ways to integrate that information so that we can build models and get better understanding of how the cortex, the mammalian cortex, actually works. These are my cells.
Productive nanosystems, from molecules to super products. Final production made possible by a challenge grant from Mark Sims and Nanorex Incorporated. Future advances in molecular nanotechnology will enable desktop appliances to manufacture products far better than today's best. The cartridges to the left supply simple raw materials to the machinery inside, here shown in schematic form. Products emerge from the top of this box, which holds the heart of the manufacturing system. Each product is built from beneath, layer by layer, by billions of tiny machines all working together. Near the top surface is the productive machinery itself, organized into layers. Machines in the lowest layer process molecules into building blocks, passing them upward to machines that assemble them into larger components, and then to machines that add these components to the product. From a millimeter scale, 1 million nanometers, our view zooms in to the 10 nanometer scale. Each box is 1/10 the size of the one before. Here, at the molecular scale, nanomachines make small building blocks from molecular raw materials. The first machines sort molecules by their size and shape, passing some, rejecting others. Only molecules of the right kind can enter the processing machinery. These molecules contain 4 atoms, 2 of carbon and 2 of hydrogen. The molecules bind to a device that carries them to the next stage. Then, a rotating mechanism swings tool tips into contact with the bound molecules. Each tip presses a molecular tool against a molecule, bonding it firmly. The tools shown here have been analyzed using advanced quantum chemistry techniques. Another tool moves in from the left to remove the hydrogen atoms, leaving a pair of carbon atoms exposed and ready to use. The tools then carry these atoms to their destination, where each pair bonds to a nanoscale building block, making a tiny bit of crystalline carbon, a bit of diamond. Motions happen quickly at this scale. This scene shows motion slowed by a factor of more than 1,000,000. A conveyor carries the blocks past further machines, which build the blocks step by step to full size. Elsewhere, other specialized machines build blocks of different kinds. A system of conveyor belts and transfer mechanisms carries completed blocks from where they are made to where they are needed. This transfer mechanism moves blocks from one belt to another. The transportation system carries many different kinds of blocks, different shapes, different materials, different functions. It delivers them to the next stage of manufacturing. Here, a programmable machine lifts and places small blocks to make larger blocks. The small blocks bond on contact to form components containing millions of precisely arranged atoms. These can be simple structural bricks or intricate components for mechanical and electronic systems. The completed components are delivered to the final assembly stage, where many machines work together to build the final product. Motions at this larger scale are still quick. This scene shows motion slowed by a factor of 10,000. At the base of each machine, a transfer mechanism grabs components and lifts them from a conveyor. Each is flipped around, then carried up to the underside of the product under construction. Finally, machines lift the components and plug them in place, adding layer after layer to the bottom of the product. When the last layer is finished and construction is complete, the product is ready to be removed and used. The result of this production run is an atomically precise multiprocessor laptop computer with 1,000,000,000 times more processing power than today's best. The only waste products are warm air and pure water.
Nanomedicine is the medical application of nanotechnology-related research. It covers areas such as nanoparticle drug delivery and possible future applications of molecular nanotechnology.
The application of nanotechnology that people are most excited about is in medicine. We picture extremely powerful medical applications, being able to analyze the body down to the molecular level, do repairs at that level, and in principle, one could address just about any disease you can imagine this way.
Nanomedicine, a book series by Robert Freitas that analyzes a wide range of possible nanotechnology-based medical devices and explains the relevant science behind their design. Freitas writes that the net effect of all nanomedical interventions will be the continuing arrest of all biological aging, along with the reduction of current biological age to whatever new biological age is deemed desirable by the patient.
You can sit here and discuss aging, and then, ultimately I will sit and discuss nanotechnology because I view them as being, what I've got to get is I've got to get 5 years, then I've got to get 10 years, then I've got to get 20 years for myself. If I get that much for myself,
So at the same time, we find how we age and we find the treatment. We need to develop nanotechnology to have the technology to apply those treatments.
That's right. I mean, ultimately we end up with nanotechnology. Ultimately then, we give you a whole new genome, or we do with the outloading, inloading, uploading, path.